All right, so we're going to start. This is the first part of rotational motion. See if my voice lasts through this. And so we're going to look and see what that's all about. So first, let's define what rotational motion is all about. And before we do that, we're going to review a little bit about what we've already studied. So in the first part of kinematics, we studied translational motion. Translational motion is better known as linear motion. That's where something is moving in a straight line. During that, we measure the displacement, the velocity, and the acceleration of an object. So that's what we've already done. So what we're going to do now is we're going to look at rotational motion, not circular motion, so not like a ball on a string or like the Earth orbiting the sun, but it's going to be like an object that's rotating, like the Earth is rotating every day. That's the kind of motion we're going to look at. And we're going to study angular displacement now, and angular velocity, and angular acceleration. So and then we're also going to relate the rotational motion to the translational motion. We were only going to be studying rigid body rotation, and a rigid body is something that doesn't transform, doesn't change into something else. So we're not going to like spin a bowl of water or something like that where the particles are not rigid, because that's all kinds of crazy physics going on there. All right, so a rigid body that rotates about an object. So this is a drawing of it's like a flat disc. The axis of rotation, it comes out of the page at point 0 or point O. I guess that's point O. And then this one's all the particles are moving in a counterclockwise fashion. When this happens, then every particle on that disk is rotating in circles. So I've got marked on here point P that follows that dashed line. If I was to put a point part way through, like here, then we would get a motion that goes around in a circle this way. But it's still going around in a circle, everything on the object. We have measurements of the radius. So the radius is from the center of the axis that's it's rotating on to the point that we're talking about. Could be on the edge, could be someplace in the middle. And then when the object rotates, then we imagine a point like that point P, and that rotates about an angle, and we're going to call that theta. When it does that, it moves in this arc length. Now, in mathematics, you probably learned a little bit about arc length, but we're going to label that L. So it's just part of the circle. Special thing happens here. If this length, this arc length, is equal to the radius, then that means that the angle has moved 1 radian. So maybe you're unfamiliar with the radian measure. The radian measure is nothing more than just an angle measure. It's like degrees. So you've studied degrees in all of your math, but maybe never the radian. And the reason why we use radian is because of this special relationship, and that's when the arc length is equal to the radius. So we're going to be doing that a lot. Don't worry, your calculator will deal with it, and we have some conversions also we can do it. On a circle, there are 2 pi radians. That would calculate to about 6.28. So if we multiply pi by 2, then it would be a complete circle, and that would be about 6.28 radians. The distance the particle moves comes about for this formula. So this says that the arc length is equal to the radius times theta. So as I mentioned, if we're at this point P, this moves in a large arc length, and if if I had another point in the middle here that moved, that would be a smaller arc length, but then it's got a smaller radius. So the arc length is directly related to the radius and also to the angle theta. So we read this as the arc length is equal to the radius times the angle in radians. Okay, so we're going to deal with how we measure that. So as I just mentioned, the circle has 2 pi radians, and that goes around, that's 360 degrees, and we call that 1 revolution. So when you get a problem, you're going to be given one of these 3 measurements for the angle, or the angular displacement. And just for your reference, a radian is equal to 57.3 degrees. We don't ever really use that number for calculations, but I just thought maybe you'd want to know what that is. About 57 degrees. Okay, so let's do a problem. A bike wheel rotates 4.5 revolutions, and how many degrees it goes. So we have this bike, and then it rolls and goes 4.5 revolutions. So now we're going to figure out how many degrees that goes. All right, well, we do that by taking the 4.5 revolutions, and every 1 revolution is 360 degrees. And so we're simply just going to multiply 4.5 by 360 for 1,620 degrees. Pretty simple conversion, but the point is you can use these relationships for conversion reasons. What about how many radians? So we have 4.5 revolutions. So now every revolution is 2 pi. So we're just going to multiply the 4.5 revolutions by 2 pi, and we get 9 pi. And it's fine to leave it in terms of pi. You could multiply that out. So that's 9 times pi, which is 3.14. So maybe 2930 radians it will go through. But 9 pi is fine. So now, but what if we knew the diameter of the bike tire is 60 centimeters. How far does the wheel go down the sidewalk? Okay, so we're going to use that formula we just learned because we want to know what the arc length is. So when this tire moves 1 revolution, it's going to equal a circumference. And a circumference is an arc length. So we simply take the radius and it doesn't really matter what unit you use in here. If I put centimeters in for radius, then my arc length or my distance is going to be in centimeters, because theta, the angle, doesn't have a unit. It's a descriptor, just like degree is, but now it's radians. So I'm going to go ahead and do it in meters. So first I watch out because it's the diameter and I need the radius. So I half that. That's 30 centimeters. I move the decimal over 2 places. So that comes out to 0.3 centimeters, and then multiply it by the 9 pi that I got there. Remember, we can't use the 1620 because this relationship only works if theta is in radians. Radius can be in anything, but theta has to be in radians. So I multiply that out, and that's 2.7 pi, or approximately 8.7 meters. So any of those units are fine. If you're going to leave it in terms of pi, 2.7 pi, make sure you put the meter after it, because it actually is a meter. Probably best in physics to end up with a number. In math, you're often told to leave things in terms of pi, but in physics, we want an actual number in that. Okay, so now we're going to look at rotational kinematics. In translational kinematics, we did displacement, velocity, acceleration. So we're going to find some similarities there. The angular displacement is the displacement of angles, if you want to think of it that way. And it's measured in radians. Most covered that already. If we wanted a change in the angular displacement, then we would simply subtract one angle from the next to find the change. Angular velocity is also in kinematics. We use this omega character. This is a Greek lowercase omega. Looks like a W, but it's not really a W. So just like in translational kinematics, velocity was the rate of change of displacement. Well, so is rotational kinematics. It's the rate of change of angular displacement. So then we're going to have omega equal to the change in theta, or the how many radians it goes and in how much time. It's like velocity, that's what I mentioned here, but now we use a direction and we either say it's clockwise or counterclockwise. Now those are relative terms because it depends on your perspective on what something's going clockwise or counterclockwise. All particles in the thing that's rotating have the same angular speed. So in that bike tire, everything connected to that bike, with the exception of the very, very center point of the axle, it was all going the same rate of displacement, the same number of radians per second when it was moving. So let's try an example here. A quarter rolls 12 revolutions in 1.8 seconds at a constant speed. What is the angular velocity? So this is the first thing we have to do before we use our formula is we have to change revolutions into radians. You'll find this is common. So one revolution is 2 pi, so I multiply the 12 revolutions by 2 pi and I get 24 pi. Then I use my formula I just learned. Omega is the change in angular displacement over time. So that's what I just calculated there at 24 pi, and it's 1.8 seconds. And so that calculates to 41.9 radians per second. Now, your reference on that is that, okay, so it's spinning around, knowing that one time around is it's about 6 radians, roughly 6. So, if you just imagine this is about 42, so it's about going 7 times every second. So it's kind of fast. It does do 12 revolutions, go around completely in not even 2 seconds, so it is quite fast. Okay, so the next thing we're going to look at is the angular acceleration. So just like in translational kinematics, we studied acceleration. And translational acceleration was how much the velocity is changing. Well, this is the same thing. This is the rate of change of angular velocity. We use the Greek lowercase alpha to indicate that. To me, it looks like a sort of a fish. And so alpha is equal to the rate of change, or the change in angular velocity per unit time. So we're going to be calculating that too. There's a couple other things as we're going to do, and that is linear velocity. So this would be like how fast is the outside of the tire going. Well, of course, that depends upon the radius, because the further out it goes, then the faster it has to go if it's spinning around at a certain speed. And so we take the angle length, or the arc length rather, and we change that to r delta theta, and that delta theta over t is omega. So the the linear velocity is equal to the radius times the angular velocity. So that's going to be in radians per second, and that's going to be in any other measurement like meters or centimeters or kilometers or something like that. So then we get kilometers per second, because again the radian is not a unit, it's just a descriptor. Now, tangential acceleration is the acceleration that's tangent to the circle. All right, so that is that would be how much this velocity is changing. So that is change of velocity over time. We take the change of velocity, r omega, we relate that to r delta omega, because that's a change in angular velocity over time. And then that is alpha. So we have the tangential acceleration equal to r times alpha. Well, there's also the radial acceleration. This radial acceleration is known as the centripetal acceleration. I had to call it that because our book, and that's how they refer to it in AP. So that is v squared over r. So I take this r omega and I square it over r. Omega squared stays, but r squared cancels one of the r's down there. So the centripetal acceleration or radial acceleration is omega squared r. And lastly, the total acceleration, and I'm just going to label that with a lowercase a, is equal to the tangential acceleration plus the radial acceleration. So I'm not going to add the alphas in there because that is not an acceleration. So we rarely will calculate things with that formula, but just so you have that in case it shows up. Okay, so an example here is we have a can of Red Bull, rolls down Legion Hill, and goes from 5 revolutions per second to 16 revolutions per second in 4.5 seconds. What's the angular acceleration? Okay, so angular acceleration, that would be alpha that we're looking for. So we need to know what the change in angular velocity is. Well, we're given it in revolutions per second, and the reason why that is because that's much easier to count or measure than radians per second. So oftentimes real data will be given in radians per second. But that shouldn't be a problem because we're just going to take the revolutions per second, each of those, and we're going to recalculate those in radians per second. The time was given as 4.5 seconds. All right, so I first figure out what the, I'm going to go ahead and just find the change in omega. So that's going to be 16 minus 5 revolutions per second. So that's 11 revolutions per second. And then I'm going to convert that to radians per second by multiplying by 2 pi. So 11 times 2 pi is 22 pi. So that is the numerator. That's the change in angular velocity. And then I'm just going to take that and I'm going to divide it by time. And 22 pi divided by 4.5 seconds comes out to 15.35 radians per second. Squared. I missed the square on that. Sorry about that. Please make sure you write that as radians per second squared. All right. So that's a very quick example. If the can's diameter is 4 centimeters, what is the tangential acceleration? So look back on your notes and you'll see that tangential acceleration is r alpha. So we're going to take the radius of 4 centimeters, convert that to meters. So we first take half of that. So it's 2 centimeters. Move the decimal over 2 places for 0.02 meters, and then multiply it by our 1535 we got up there, and it comes out to 0.307 meters per second squared. So this is how fast the outside of the can is increasing its speed. This is how fast the revolutions per second are increasing, but of course in radians per second squared. Yeah, a little bit confusing, but you can maybe see some use for the formulas we got on the last screen. Okay, so this screen is, shows the relationship between the linear kinematics that we learned. So look on the right side here, we have velocity equals VO plus AT. So these are the big 3 equations, shortened a little bit. And this bottom one is just basically the average of the velocities, so we just add them and divide by 2. Well, look at what happens over here. So we take every x that's in the linear formulas and we change it to theta. So here's one here, here's one over here. So all of those are changed to theta. We take all the velocities and we change those to omegas. So it's translated directly that way. And then we take all the acceleration A and change that to alpha. And so we have this whole set of formulas, and they come directly from the kinematics that we learned in linear motion. These two on the bottom, these are just what your formula sheet looks like. So it gives you these formulas just like they did before. That one's here and this one's here. Probably this one is also there. Maybe I just forgot to put it on there. We'll look for that. So that's pretty good. So we can do some problems with those. So a tangerine is rolled down a sloped sidewalk. If it was initially going at 10 radians per second and its angular acceleration is 1.5 radians per second squared, what will its angular displacement be in 6 seconds? So you have to figure out what you have here. We have angular velocity, we have angular acceleration, and then we have a time, and we're looking for angular displacement. So we list the givens. This is the beginning. This is what it is going initially. And there's the increase in angular acceleration, and there's the time. So you look for a formula. You look back on here, and you look for a formula that has those, and one that's where you're trying to find angular displacement. Yep, we use this one. So the theta is equal to the initial theta plus omega t plus 1/2 alpha t squared. So this one's pretty straightforward, and just plug in the numbers. Theta 0 is 0. And then we have 10. These units do not need converting, so they're all in proper units. So we have 10 and 6 seconds, and then we put 1/2 1.5 6 squared. Throw that in your calculator, and it comes out to 87 radians approximately. Okay, so in that 6 seconds, 87 radians, you could roughly divide that by 6, and you know how many times around it went. Interesting, huh? Okay, one more example, and that is a turntable is spinning at 33 RPMs, and you turn it off and count 4 3/4 times that it goes around until it stops. What's the angular acceleration? So we're given the initial, what is RPMs? Revolutions per minute. Well, that would be angular acceleration, wouldn't it? Angular velocity, but it's in a strange revolutions per minute. So we're going to have to do some converting on that. 4 3/4 or 4.75 revolutions, that would be how many times it goes around. So, but it's in revolutions, so we're going to have to do a conversion on that. And we want to know what the angular acceleration is. So you look at your formula list, and you should come up with this one, because we also know one other thing. Because it stops, then we know that the final omega is 0. So this is going to be pretty easy. I think the conversions are the hardest. So we take 33 revolutions per minute, and I write it like this so I know whether I'm multiplying or dividing. All I need to do is change the minutes to seconds, so I'm going to end up dividing by 60. And then a revolution I'm going to change to radians by multiplying by 2 pi. So that comes out to 3.46 radians per second. We also need to convert the delta theta into radians. So we'll do that simply by multiplying the number of revolutions by 2 pi. So we have 29.85 radians. Now we're ready to plug in for that. Okay, so then we take this and we plug in what we have. Keep in mind that it stops, so we're going to have a 0, and then equals 3.46 squared. Watch out for that square. 2 alpha times the change in theta, 29.85. So to calculate this, do some algebra. we're going to square, move the 3.5 over, 3.46 over, right? And then divide by 2 and divide by 29.85. And that will give us the angular acceleration of negative 0.2 radians per second squared. Negative indicating that it stops. So it was going, this turntable was going 33 RPMs and then it goes down and stops. So that would be the angular acceleration. Okay, so that's it. Contact me in the usual way if you have any questions. All right. Thanks for listening.